Let's talk a little bit about random number generation, and in particular how ExtendSim makes use of random numbers. We'll go through a sequence of 4 main sections. The first is a discussion on random number generation itself. This will be somewhat general. There will be parts of it that will be specific to ExtendSim. But we need to get some background from this particular area that we can use in the next section. Second section, we'll look at how random numbers are accessed in ExtendSim blocks. What kind of mechanisms are in place to allow us to draw random variates from within a block. Third section, we'll be looking at the same kind of concept, but looking at how we can use database cells to hold and supply random variate sequences. And lastly, we'll take a look at a few do's and don'ts and a simple example that hopefully will exhibit 1 or 2 of the do's and don'ts that we're going to be talking about there. So let's go ahead and get into the concept of pseudo-random number generation. And again, I'm going to try to refer to this particular capability as pseudo-random number generation as opposed to random. I hope everybody is comfortable with the fact that since we're dealing with a computational form, we can't claim that what it produces is random. Hopefully it behaves in a random fashion, but we'll refer to these as pseudo-random number generation methods. In ExtendSim, their recommended a generator of choice is one that's referred to as a minimal standard random number generator, and it's based on a series of papers that are referenced here and also in the user's manual on page 279. I'm sorry, page 667. And the particular form, the logical form of this particular generator is listed at the bottom of the page, and it indicates that we're looking at basically a recurrence relationship that's multiplicative in nature. There are some forms of generators that are essentially linear or mixed congruential. It includes an additive term. This particular generator does not. So essentially it has this particular form, and essentially the values that are returned are modulus some constant, and we'll talk a little bit more about that. The ExtendSim generator uses a multiplier of 41,358, and the modulus is 2 to the 31st minus 1, or about 2.15 billion. The other requirement on the generator is that all numbers in the sequence that's generated by this have to be positive. 0 is not a candidate for the starting value. If you were allowed to use 0, this thing would return a endless stream of zeros as you made additional calls on it. So this is basically the form of the generator that's used in ExtendSim. If you like, you can look at the paper by Schragi to get the actual computational form that's used by ExtendSim. It's much more complicated than what's shown here, but the end result is being equivalent to this particular form. The literature supports the claim that this particular generator, using these constants, has full period. And by that is meant that it will take on all possible values in the range from 1 to this number minus 1 before it repeats. But it will repeat after that many calls. So the period for this particular generator essentially is m minus 1. And we talked a little bit about the fact that 0 is not allowed, so 0 will never be generated by this particular generator. So the numbers that are generated are between 1 and m minus 1. I'll refer to I sub 0 in the following pages or slides as the starting stream seed. And in fact, on a couple slides later, we'll take a more detailed look at the concepts involved around that. All right, let's take a look at a little bit deeper into how the generator is used in ExtendSim. And essentially what's happening here is the actual system stream, which is the stream that's produced from a starting stream seed using the generator we just saw. I'll refer to that as the system stream, and essentially that sequence of observations or numbers is based on the setting in the dialog associated with the simulation setup. And we'll talk more about that in a minute. But that stream, you pick an I0, and then that is used to seed or choose your location in the stream, essentially. Now, one thing that's true in the ExtendSim context is that this particular stream is seldom used directly to generate PRNs. And we'll see more about that in the slide talking about custom blocks. Well, what is used to generate random numbers in ExtendSim is essentially subsequences of this system stream. And the net here is that for each ExtendSim block that wants to produce random variates, or for each database cell that has a random definition, we're going to pick a starting point in the system stream as the starting point, the seed for each of these components. And these, I'll refer to that as with the quoted term stream or streams to indicate that what we're talking about there is a specific subsequence that is allocated to a block or a database cell. And the assumptions, or some of the assumptions around that, is that each of these streams should be unique. They should be unique from each other in the sense that since they have a different starting point in the system stream, they'll generate a different sequence of random numbers than any other. There's consideration that we need to keep in mind, and we'll look at it a couple different times, and that is essentially nothing is done to keep these block streams and cell streams from overlapping. And what that means is that it's possible for two or more of these streams to share the same subsequence of the system stream. And that's the term that we use saying overlapping. Now, it's difficult to determine the number of draws between the start of one stream and the start of the first stream to be overlapped. It's a fairly complex problem in terms of how you determine where it is with respect to the nearest stream that might be overlapped if you kept drawing. And to illustrate what we've just went through in the first three slides, I want to look at this particular slide in some detail. Now, here, what I've done is to select another instance of this minimal standard random number generator. This time, I'm using a constant, a multiplier of 11, and a modulus of 23. This will be essentially a useless generator, but at least it illustrates the issues that we're looking at in terms of this, the way the blocks and database cells use portions of the system stream. On the left here, we've listed, I think there's a total, in this case there's 26 draws on the random number generator. We're using a seed of 5 for the system stream. And so when we plug in 5, multiply it by 11, and take the modulus against 23, we get the number 9. So that's the next sequence. That's I1. That's the first draw given a seed of 5 and this set of constants. And so you can see it's 9, 7, 8, and you can follow it down. And finally, after the on the 22nd access to the generator, we see 5, 9, 7, 8 again. So it does repeat. This has full period, and the period is 22. It's m minus 1. We'll get there's a total of 22 distinct, unique values that are represented here, and they appear exactly once before the stream repeats. So this stream represented by the I variables here is referred to as the system stream. Now, in terms of utilizing random number streams, you never want to ever get close to exhausting a stream. So you'd hope that you never end up with a model that would ever use more than, say, half or 2/3 of the available draws in a stream. So in other words, in terms of the ExtendSim generator, if you're getting over 1 billion or so random draws, then you're probably getting to the place where you're getting awful close to problems with respect to repeating again. So we've talked about the system stream, and that's based on the starting system stream seed. In this case, it's 5. I can use any one of these 22 values as I0, and all I'm doing is just picking a different starting point in this endless stream, essentially. Now, in terms of substreams or quoted streams, as we referred to them on the previous slide, let's say we have a random number block, and it's supplying random variates of some particular type to, in this case here, a set block. It's going to have its own block stream, and that block stream is going to be defined by the seed that's established inside this random number block, and we'll talk more about that in coming slides. But if it turns out that this block's starting seed is 8, then it's going to start generating in this portion of the system stream. So we're going to call the stream of numbers we get using 8 or F0 as the starting seed. That's this block's quoted stream. And indicated here that the block made maybe 5 different calls to generate a random number. So it took 5 draws on the generator. Likewise, if we have a database and we have assigned or defined a cell as holding a random distribution, in this case the normal, mean 200, variance 25, then that particular cell, referred to as database cell, is going to have its own unique stream. And essentially that stream is going to have a starting seed somewhere in this set of system stream values. And I've denoted that one by K0, and indicated that K0 was 6 in this particular case. So it's going to generate a sequence of numbers. First number it'll generate is 20. Next one's 13, 5, and I've shown it up here again as continuing 5, 9. There really is only one set of 22 numbers. So once we hit the end of it, it just keeps repeating in that particular context. Now, you can kind of see in this area here the problem we were referring to on the previous slide. Let me go back to that one. We indicated that said that nothing is done to keep these streams from overlapping. And essentially, that's what we're going to be seeing in this particular case. If instead of just requiring 4 draws, if we read this cell 6 or more times, it's going to end up needing 6 or more numbers from our stream. So if it on K6, it's actually going to find the exact same value as F0. On K7, it's going to find the first value that was used for this block to generate a random variate here. So that's the beginning of an overlap. If this particular stream requires more observations than, well, if it's sufficient to get to the place where the next stream is located, that's an overlap. Now, that particular condition may or may not be detrimental. It just depends on the way the 2 streams involved are utilized in the model. But suffice it to say that once you get to the place where you're overlapping another substream here, you're running the risk of problems associated with higher order serial correlation. So it's something that you need to be aware of, but it's at the moment it's fairly difficult to to detect and to control. Before I leave this particular slide, I want to just indicate the notation we'll be using in the rest of the discussion. When we talk about the system stream, we're talking about the sequence of numbers based on the starting system stream seed that's supplied through the mechanism of the simulation setup dialog. That's what's defining the system stream. The block streams and the database cell streams are essentially different, use different seeds to start where they're going to be generating, but they'll generate a sequence of values starting from wherever their particular seed is located. So we've got one system stream, and we'll have many block streams and database cell streams. So that'll be the concept or the context that we'll be into in the following pages. Okay, how do we access the ExtendSim generator? We talked about the system stream seed. It's referred to, or there's a parameter in the dialog of the simulation setup dialog that is used to set or control how the system seed is determined. And we'll talk a little bit more about that on further slides, but I'll refer to that as RANDOMSEED in CATS. And that's essentially that's the global variable name in the ExtendSim application context that always remembers what that setting is. And there's two different ways to set that or control it. One is to either set it to 0 or blank, in which case we're asking for the starting system seed, stream seed, to be randomized. And by randomized, we mean that every time a new run starts with the setting set this way, we'll make a call to a system clock to get a new starting value, starting seed for the system stream. That's the randomized version of it. The fixed version is to choose a constant between 1 and m-1, where m is actually this should have been 2 to the 31 minus 2. So that's the way that's set for identifying a fixed starting stream seed. And we'll find out that when we use this particular mode, when we set it to a non-zero value, that value will persist for all runs of a multi-run set. Now there's a third way to set this, and that is by referencing a database table called _seed that supplies starting system stream seeds for multiple runs. I'm not really going to talk about that any beyond this particular point, but just be aware that there is that third method for which to use to establish the starting system stream seed. Now, next thing is there's a couple of API or application programming interface calls that are used to get or set the current system stream C. One thing we probably didn't mention in the previous slides was that the result of calculating the recurrence equation generates both a new observation random value. It also produces the seed for the next time we call it. So the seed is perpetually produced by the last time we call the recurrence equation. So these two API calls first allows us to get the current value that is being used for the system stream C. Second is a way where we can actually set that. And we'll see these in use in the next few slides here. Next area here is how do we actually cause a new draw on the PRNG? And essentially there's only one ExtendSim API call that does that. And that's this call to random real, which ends up doing it, generating the next value in the sequence, which is an integer number between 1 and m minus 2, and then transforming that into a real, a uniform real between that includes 0 but does not include 1. So one thing you need to be aware of is this random real will never return a value of 1. It will return a value of 0 with probability 1 over m minus 1. So this is the only way that you get an actual call to the PRNG. So the PRNG is internal. All these other methods are higher level. Now there's a whole list of API calls that can be used to generate variates from various distributions, and all of them will end up using one or more calls to the random real function. For instance, there's a d-exponential API for generating exponentials. There's a general form called random calculate, which allows you to specify which distribution you want and what its parameters are. So you can use this form here with any of the 30-some odd distributions that are available within ExtendSim. So summarizing this particular slide, we have a way of initializing the starting system stream seed. In fact, there's several different ways. We have a couple different API calls that we can use to get the current seed or set the current seed. We have exactly one way to do another draw on that generator, the random real, and we have a bunch of different ways that we can generate random variates which use transforms of one or more random reals. All right, let's take a look at let's switch to the block context next. When we're dealing with blocks, let's say we're dealing with blocks that need to generate random variates, and essentially the random number block is a good example. We'll end up seeing a signature in all of these blocks that looks something like this. There'll be a dialog setting here which allows you to to check something called use block seed. And if you do, you can then set the parameter or the value that you want that block to use. If you check this box, if you check that checkbox, in essence, you're isolating this block's substream from the system stream. In other words, if the system stream is being randomized, in other words, from run to run, you're choosing a different starting value, and you specify in this particular block that you want to use a particular value. This particular value will override. In other words, the block will not use a different stream on multiple runs. It'll use the same stream on each of n multi-run simulations. The issue that comes into play with respect to that is you may have one or more blocks that are using the same block seed, and that's an issue that you should be aware of, and I'll show you in the system simulation setup dialog how to control that. When you leave this unchecked, as it is here, what you're doing is you're ending up setting up the starting stream seed to be a function of the starting system stream seed. If you remember back on our previous sheet there, we had a system stream seed of 0 starting of 5, and if this block number is 35, then we'd add 35 to that plus 1, and that would become the starting stream seed for this particular block. What we're doing is we're choosing and hopefully an independent spot in the system stream to start our sequence of random numbers. And essentially, if all the blocks in the model use this method, we can ensure uniqueness of each block's starting stream seed. Again, we can't say anything about overlaps. All we can say is that we've ensured that no two blocks use the same starting point. And essentially, the calculations to do this setup is usually done in Initsim. So we'll run through the settings in Initsim to actually establish the block seed for each block that has this particular mechanism. When you get to the place where we're wishing to generate a new random variant from some distribution, the code that takes place there in these standard ExtendSim blocks is we'll read the current, we'll get the current system seed and save it locally. We'll set the system seed to our current value of block seed for this particular block. We'll then call the appropriate API call to generate the variants that we're interested in. And again, that may involve more than one call to the PRNG. When we've completed that, we then reset things. We'll basically save a copy of our block seed, which will have changed because we'll have drawn one or more PRNGs. So this number at this point will be different than it was at this point. When we save that, we'll then reset the system stream seed to what the value that we saved it at. So this particular mechanism here makes us transparent to the system in the sense that we don't disturb the system seed. And if you remember back several slides back, I indicated that in ExtendSim blocks, you very, very seldomly actually draw directly from the system stream. You always are dealing with the local isolated substreams on a block or database basis. And again, here's some examples of the API calls for that. Okay, so some of the considerations for custom blocks here. If you're building a custom block which needs to call a random variable producing API, you should make the effort to isolate the custom block's stream from the system stream. Use of the structure of the equation block in the value library will give you a good reference for how this is done. You can, if you open up the structure of the equation block and follow the uses of the variable mySeed, you can see the places that you'll need to make code changes or code addition to accommodate the standard code practice from ExtendSim. The question comes, what happens if you don't use the standard code, but your block is still making calls to the to generate random variables? If we go back here and look at this particular code section here and envision that we didn't have this set, these before and after sets of code. We're just drawing variables at one or more places in our custom block. If we do that, what's happening is that we're actually fishing in the system stream and not in a stream that's isolated for this particular block. And the question is that a bad practice? And the answer is both yes and no. It depends on how things are being used in the block. But in general, my recommendation is that if you're building a custom block that needs to generate random variables by a code as opposed to accessing a database, then you probably should use the standard code practices. We can talk more about that in the question session if there's an interest there. Other question is, what if you need more than one stream within a custom block? The standard code method here, which basically sets up one isolated stream per block, doesn't work for us anymore. So what we'll do is we'll see, when we get into the next section on database methods, we'll see that using that kind of capability gives us the ability to deal with as many streams as we need in the context of a custom block. All right, so let's switch gears and go to the database mode. And now what we're going to do is we're going to look at the methods and so forth that apply when we essentially define a cell as containing a random distribution. And for those of you that haven't been through it, what you do is you right-click on a cell, and that pops up a menu option, and the very first entry on the menu is Make Random. If you choose that, you get this database random distribution dialog. And what you can do here is define which particular distribution you want, specify its parameters, and then hidden behind this guy here is a button that says plot distribution. And I recommend that you use that button to get a plot so that you can verify that it really is the distribution you want. Occasionally you'll find out that you need to include a location parameter to get it moved, shifted one way or the other. So use that the plot distribution capability to help you out on that. But when you're satisfied with the distribution and you click on OK, you'll see that cell, what shows in the cell now, which used to be 200, is a string that indicates that we have a distribution set, in this case normal of 225. So that's the way random distributions are set in database cell. Now, I want you to notice that on the bottom of this database random distribution dialog, you see the same signature that we saw on the block, like the random number block that has essentially a checkbox and a parameter, which can be used to essentially override the system method of whether or not you're dealing with a randomized starting seed or whether it's a fixed seed. In either case, you can actually, if you check this box, what you're doing is you're separating this particular cell's random stream definition from the system definition. If the system is randomized and you click on use seed and specify a number, then that number will be used as the starting seed for this particular cell on every run of a multi-run simulation. Now, it's possible to, let's say you had set the model up to run in a fixed seed mode, where every run of a multi-run simulation is going to use the same starting system seed. If I check this and put 0 here, then what that's going to do is it's going to actually randomize this particular cell's starting seed selection. So from run to run, if I did that, if I checked it and used 0, it's not going to use the same starting seed value on each run of a multi-run set. If we leave it unchecked, then what's happening at that particular point is very similar to what happened in the context of the block. The two differences is that the seed setting is associated with this cell and not with a block. And the second is that instead of using a block number as an offset, as we did in the block number case, we're using 2 million plus how many ever database cells are random as the offset. Now, that's a little hard to pick up in verbs, so let's take a look at some simulated or some pseudocode here for that particular process. This is the code that's used to initialize all starting stream seeds for cells with a random distribution defined. And what happens is, the first thing we do is we set a global variable equal to the current system seed, whatever it happens to be, this would be the starting seed at that particular point, starting system seed. And we're going to add 2 million to it. So we're offsetting by 2 million. Then we're going to go through a set of 4 nested for loops, where the outer loop is for databases, then tables, then fields, then records. And we're going to end up determining whether a particular cell that we're pointing at has a random definition or not. And if it does, then what we're going to do is we'll use that, the current value of that global variable as the starting cell seed for that particular cell. And then we bump it so that the next cell will get essentially 2 million plus 1 as its offset. Now, some things to note here is that when we're looking at databases, we go out and we say, okay, how many databases do we have in the model? This returns the total number that the model has ever known about. But some of those databases may not be active. So we have to first test to see if the particular database we're pointing at here actually exists. And if it doesn't, then we do a continue, which basically skips all of this code and gets us the next database. If it does exist, then we do a check on how many tables we have in this particular database. And again, there may be, this may be a number that's greater than, there may be some tables that don't exist. So again, we have to check to see if this table exists in this database. And if it doesn't, we do a continue, which skips the rest of these, this code for that particular case. If it does exist, we get we go through the individual fields for that particular table, and then within a field, we go through the individual records in that particular field. And if we find that the cell that we're pointing at, the database table, field, and record, is not a random definition, we do a continue, skip this particular set of code. Otherwise, we'll actually set the seed for that particular cell. There's these two API looking things here are just they're my terms for what actually is happening at these two places, and are not really the API calls that are being used at this point. But the net result is that when this particular code is run, we're going to go through and essentially initialize the starting seed for every cell in the database that has a random distribution defined. So that's essentially done using this particular code. The question now is, when is that done? So if we take a look at this table or this page here, what we're looking at is the steps in a multi-run initialization. In other words, for every run of a multi-run simulation, these are going to be the steps that we take during the initialization process. The very first one is to set the starting system stream seed. And here's the use of that random seed parameter that we talked about earlier. This can either be 0 or blank, or it can be a positive value. If it's 0 or blank, then what we're going to do is we're going to set the starting system stream seed to essentially the current value of a millisecond clock. This is what will actually take place in 802, in 801, what's being read here is the 60 hertz clock. So you go out and read the current value of that particular clock and use that as the starting system stream seed. If the random seed value is positive, it's 451 or 21 or whatever, we're going to use it directly to set the starting system stream seed. So that's done at step one. That's the very first thing that's done on each simulation run. The next thing is we're going to go through that code we just saw on the previous page to set all the database cell starting stream seed. So that's done at step 2. And then step 3 through 8, we'll get into the standard system messages or events that each block is able to respond to. Some of you may not be familiar with SimStart, but it is the very first of these messages that's passed on to each of the blocks. Pre-check data and so forth. During InitSim, we'll see that this is the normal place where blocks end up setting their starting system seed. Some blocks will do it earlier depending on their needs, but normally it's done during InitSim. Again, the sequence that occurs at the point in time when we are reading a database cell is very similar to what we saw in the block. We'll save a copy of the current system stream seed. We'll set the seed to the cell seed that we're keeping. We'll do our API call. This API call is always done through that random calculate method, where you're specifying which particular distribution number it is and what the parameters are. When that's done, you then reset things so that the system stream seed is untouched. And that's pretty much the way that you actually obtain a variant. The API call, or one of the API calls to get that variant, is to do a DB data get as number. You specify the database table field and record, and if that cell is a random definition cell, like real, uniform, or exponential, or whatever, we'll actually go through this particular sequence to produce a number that's returned as this value. There's 2 or 3 other database API calls that produce the same thing. Okay, so let's talk a little bit about best practices here. I would recommend that you do not share or reuse random variables. This is a fairly common practice, but it has a number of potential side effects, so I'd recommend against this. So end up using separate generators that reads independent streams for each different random context, and we'll see an example on the next page. If you're in a database context and you have several different contexts that want to use a normal, the same distribution, you can use what's called the named distribution method, when you're on that random distribution dialog, when you're setting up a cell, you can select whether or not that is pointing at a named distribution, where you can give a particular distribution some name that can be referenced by other random context cells. But the key thing here is that each cell will have its own independent stream, as we've seen in the previous section, even though it's using a common named distribution. Second thing is, do use the standard code when you can to define a stream, an isolated stream for custom blocks that are generating random variables. Again, you can refer back to that custom block slide. If it turns out that all of the random distributions that a custom block is going to need to access are housed in a database, or one or more databases, then you don't need to actually assign a block stream for this custom block, because all of the random distribution definition cells will have their own stream identified. So there's no need to use a block stream if you're going to access everything through the database. So that's a savings, and in fact this is a recommended way, if you have a choice, is to put the stuff in the database and save the code in the custom block to just being DB data get as number type access. The last one that's listed is use the capability in the simulation setup dialog to check that all of the starting stream seeds are unique. This is a very, very handy tool, and I recommend its use as a standard practice. All right, kind of gone through the slides here. I wanted to try to go through briefly a little example to give us a little bit more of a look at some of these topics. So what we're going to look at is a little model where essentially this company called Acme Packing has asked us to build a model to test their new packet H block, which accepts items carrying a length and width attribute. And their OR department says that the way we should test it is to generate items representing packages that have a length and width drawn randomly from a uniform distribution over 1.5. And their suggestion based on analysis says that we should see an average of about 12 packages per container. So let's look at a model. Wait till everybody's there. We go. Okay, so here's their H block that they've given us, and they've asked us not to take a look at it because it's supposedly proprietary. But so what we've done is basically set up a model that's going to generate packages, and I've got this set so it's going to generate one every, the interval between generations is 1 time unit. And for each item, we're going to take a draw on uniform 1, 5. These distributions should be the same. And one will be assigned to the attribute length and the other to the attribute width. And then we'll pump that in there, and it's going to do its packing method, try to see if it can pack these packages into a container. As soon as the container is full, or as full as they can get it, they'll release it, and then we can measure how many packages were part of that particular container. So let's take a look at, let's run this. Well, let's first see the run simulation setup. Okay, I'm going to run this for 1,000 time units. I'm going to make 10 runs. I'm not specifying a random number, so we're in the randomized mode here. So each of the 10 runs will use a different starting system seed. I've set the checkbox here to check for duplicates, so that in the random number generators I've got a couple here, and I'm guessing there's probably some inside here, but I don't know that. That it'll check to make sure that everybody's substream is unique. So let's go ahead and run that. And now let's look at the stats. What we've done is we've captured the average number of packages per container in an MMV block, and then we've got the stats on this. So if we look at the, I'm sorry. What it's saying is that we've got a little over 5 plus or minus 0.07 packages per container. That's well below what they suggested was their expectation, which was around 12. Now, one thing we could look at is to convince ourselves that we are specifying rectangles as opposed to something else. And so here we have our first package was 1 unit length, 3 units in width. Next was 5, 1, and so forth. That looks like that's random. So before we leave this particular slide, if you remember, we indicated that it's not a good idea to share random variates. So even though I'm drawing from the same distribution in 2 different places, I'm doing it in 2 different blocks or on 2 different cells of a database. We'll talk a little bit more about the rationale behind that in a minute, but if we were to try to reuse random variates, we're going to bump into some issues. We may end up running just fine, but it might be inappropriate. All right, so let's go back to the so we didn't hit our target for 12. So we mentioned that to the OR department, and they say, okay, they suggested testing with squares rather than rectangles, as we had in this particular case. So squares with sides from 1 to 5 uniform. And they say that you should expect about 10 packages per container. Now, I've got the solution here, but I'm going to show you how it's produced. So I'm going to go back to this one, and I'm going to violate my rule on reusing random variates. So at this point, now I've got 1 generator instead of 2, and I'm going to be using that number in 2 different places, and I'm expecting that this should generate squares. In other words, the same number I use here should be the number I use there. So let's see how that works. Seems to run, so it must be okay. Didn't get anywhere. It's no different in appearance here than it was in the previous case. Still around averaging 5 packages per container. Well, let's take a look at our, and we should be seeing squares here, but we're still seeing rectangles. We should have seen 5 and 5, 1 and 1, 4 and 4, and so forth. But we're seeing essentially 2 different values showing up here. This is it's a classic issue with respect to connectors in this particular form, and I'm not going to go into the rationale behind this at this point. We may in the questions if that's of interest to people, but suffice it to say that the random number generator is not being sampled once per item, it's being sampled twice. Once when the item gets here, and once when the item gets here. And since it's sampled again, we're getting a different value for the width rather than the length. So that wasn't very successful. And it does violate our first don't in terms of not reusing random variates. So let's try a different approach. The solution is contained in this particular one here, but I'm going to build it. The first thing I'm going to do is I'm going to revert the model to its prior version with 2 generators here. And if you remember our statement that if we click this, then the block is going to use this as its starting seed. And if I can have both of those generators using the same exact seed, then I should be able to generate squares. So I fixed that one. Now I've got to change this one to 2 because that was the value that the other generator is going to be using. So at this point now we have both of these generators supposedly generating the exact same sequence of variables. So now let's see what happens. Whoops. Our check there caught us. It says that we have at least 2 streams that are identical in the model. Now this should also be checking against database cell streams as well. Okay, it points us to which 2 they are, but we know which 2 they are. So I want them to actually be identical, so I'm going to relax that check here. I'm going to uncheck that box to have them verify that they're unique there. I'm going to run it again. This time it ran. Now, first off, let's check and see if we got squares. And looks like we did. We got so by using 2 different random number blocks, we're generating the exact same stream. And we did that by forcing the block to be fixed and essentially forcing the second block to be fixed, but also using the same starting seed as the other block. So these 2 here are generating the identical same stream, and our check in the first case there was actually telling us about that. Okay, there's a couple more things we could try, but I'm going to leave that to the student. One thing that you might be interested in trying is a single generator into a set block with setting both of the attributes in one set block. And you'll find that there's some interesting behavior in that particular one as well. Okay, so maybe after all that's done, maybe it isn't our model that's at issue, but maybe it's what's inside the packet H block that's the problem. So let's take another look at that. It says it's proprietary, but it sure doesn't look like it's much. All that's being done in this particular block is we're using a batch block with a random number of target items. In other words, the first time in, we might ask it to batch up 5 items. Next time it might be 7 items. Next time it might be 3 items. So this doesn't look like it's much of a packing algorithm. So either the OR department didn't give us their latest, or they're trying to hoodwink us there. But anyway, hopefully you can use this little set of models to play around with and learn a little bit more about the issues with respect to use of random numbers, and also some of the issues surrounding connectors. I've taken a heck of a lot more time than what I thought it would be, and I apologize for that. But hopefully there's some utility in what's being presented here, and I'd like to turn it over for questions at this particular point.
So if there's any questions, please type them into the question box, either something about the random distributions or about simulation in general. I'm available to answer those. Lynn, thank you very much. That was really helpful. Really got into a lot of good details about how random distribution works, and I liked your example in particular. I think if, with your permission, I may borrow that in the future.
It's also proprietary.